So let's start. Okay, so thank you, Jelani. Thank the organizers for inviting me. I'd like to tell you today about work we did with Ishai Chaviv about something called the restricted isometry property of subsampled Fourier matrices, and I'll go in a slow pace. I don't think I'll be able to fill the entire hour, so feel free to ask questions. And this is, so this is answering Sasha's question. This is Fourier's tombstone in Paris. I actually went there to take the photo, except I went to the wrong Fourier. It turns out there were two famous Fouriers. But this is the right one. This I stole from someone on Google. But yeah, so next time you go, make sure you go to the right Fourier. So what is the setup? So let me just motivate the equation. It's something called sparse recovery. So let's try this mega chalk. Basically, I have this fat matrix A, and you want to have the magical property that you can recover X given AX. Or obviously, this is impossible because the matrix compresses, right? AX is a very low dimension compared to X, but the idea is that you want to recover X from AX when X is sparse. And sparse means there's a few small number of non-zero entries. You can see it there in the picture. Okay, so you have a vector X. X has some number of non-zero entries. And and you get a low dimensional vector. You want to kind of recover X. And that's actually very useful. It has lots of applications in applied math, signal processing, compressed sensing, streaming, coding theory. Actually, I don't really know what everything is, but they tell me this is what the applications are. And some of those we might hear about more later. And it's kind of nice. It means that, like, imagine you want to understand a long vector, and often in nature, in practice, they say the vector is sparse. Pictures, for instance, are usually sparse in the right basis, and you want to compress them. You don't have to store the information. You only want to store part of the information. That's the idea that you have here. Okay, but anyway, this is a very nice concept. It should have other applications. So if you haven't seen it before, it's good to keep in mind. Again, that sometimes if you have some assumption on X is sparse, you can recover X from AX. Is it clear? So this is sparse recovery, but how do you actually do that? First, how do you come up with a good matrix A? Matrix that allows you to do that, and of course, A should have some properties. If A is zero matrix, or not all matrices would do it. And B, the other thing you want to make sure is that you can actually, for us in computer science, I want to make sure I can do it efficiently. There's a way to recover, efficient way to recover X from AX, an algorithmic way to do that. And the key to all of that is something called the restricted isometry property, and that's our goal today. This was introduced by Candes and Tao in 2006. And it's a very simple property. They say that a matrix has this restricted isometry property if whenever you take a k-sparse vector X, namely vector with only k non-zero entries, the norm of AX is roughly the norm of X. Okay, I won't make it precise, but up to some 10% or something, they should have the same L2 norm. Okay, and if you think about it, what it actually means, what kind of matrices preserve norms? Well, those are the kind of isometries, right? Or orthogonal matrices. So basically, what this tells you is that, well, obviously this cannot be an orthogonal matrix; it's a very fat matrix. But what it tells you is that whenever you pick a small number of columns here, say k columns, those columns would form a matrix that's kind of orthonormal. The columns are of unit norm and kind of orthogonal. Okay? And that's a property you want. So the property they defined is RIP property, restricted isometry property. Just basically says that you take this big matrix, but whenever you look at a small number of columns, at most k columns, they're kind of orthonormal, right? Unit norm and orthogonal. And once you have that, this is equivalent to saying this, the norm of AX is roughly the norm of X. Okay, you see that? And suddenly, so why do I suddenly talk about this RIP property? Well, it turns out, and it's not difficult to show, I'll show you how, this is what they prove, that if you have this RIP property, you get what I told you about before. You get the sparse recovery property, okay? You're able to do sparse recovery. You need RIP for order 2k, for sparseness 2k, to get sparse recovery for order k. And the proof is actually very easy how these two things relate. So think a second. I need to give you a second to think about this. If you don't see it, let me tell you. So I want to show that you can recover x from ax. So imagine that you cannot. Imagine the map is not injective. Imagine there are two vectors, x and y, that are both k-sparse, and they're both mapped to the same image. Both are mapped to ax equals ay. But then, then a times x minus y is 0. Okay, it's a linear operator. Okay, but x minus y, the vector x minus y is 2k sparse because it's a difference between two vectors, each of which is k sparse. So obviously k minus y is 2k sparse, only 2k not 0 entries, right? But by the assumption, the norm of x minus y is similar to the norm of ax minus y, but ax minus y is 0, so x minus y is also 0. And that's basically the whole proof. What's slightly more interesting and surprising is they also show that once you have RIP, not only this thing is possible, but in fact, this is also something you could do efficiently. So there is a convex optimization you could efficiently solve that given ax recovers x. It's actually also not very difficult to see. It's basically you can apply L1 minimization, find the vector x of the least L1 norm that satisfies that its image is ax, the given ax. You can think about this. It's not very difficult to show why this is the case. But these data, there are lots of methods. There's a whole literature in doing that. There are lots of practical methods for doing that. This is a big topic that I will not talk more about. Okay, but this is just remember what RIP is. Okay, so back to our question. How do you come up with the matrix A that's good, that has this RIP property? And usually the main goal is to minimize number of rows. Okay, so if my whole matrix is just a big square orthogonal matrix, that's not interesting. You can always take an identity or something, right? Any k columns will be orthonormal. The trick, what you want is to minimize the number of rows, right? You want to make this matrix as short as possible. Of course, that's the goal, and that's the game will try to the question will try to answer today. And in a sense, the question is solved, and the solution is, say, as you might guess, what matrix would you choose? What's the matrix you like most? Random, right. So we all like random matrices because they behave so nicely. If you take a random Gaussian matrix, say each entry, all the entries are IID Gaussians, standard normal variables, then it turns out it's very good. And that's what you would expect, right? Because the entries are IID normal, you expect columns to be roughly orthogonal. It's not very surprising. You need to prove a few things, but what you end up getting is something like that. You get the number of rows is essentially k log n. So for random, you get say k log n. That's excellent. That's really great. Okay. So at this point, I could maybe just stop the talk because we have a very good answer, and this is also tight. This is the best you can hope for. Also not very difficult to show. Well, okay. So let's ask. So what am I asking here today? Turns out that this is not the end of the story, because if you actually want to use sparse recovery, you want to have matrices that have some structure. Random matrices are not always good for various reasons. Turns out that what people often care about are matrices that are obtained from the discrete Fourier transform matrix by choosing a subset of the rows. And that's the object we'll actually be focused on today. So imagine now I take a square matrix. This is the discrete Fourier transform matrix. Let's call it M. And this is a nice matrix for many reasons. One nice feature of the discrete Fourier transform is that you can efficiently multiply by it, using the fast Fourier transform. So we like it, we like it a lot from application purposes because it's efficient. And the question we're asking today is, if I take this matrix, yeah, good. You don't need to know, but I can define it, yeah, because we'll see. Actually, we don't. Yeah. Actually, all I need from this matrix, I'll mention this in a minute. All I care about is that it's an orthogonal matrix, okay? So like unitary matrix, and that it's flat in a sense that all the entries are roughly the same magnitude. So here, all the entries are a plus one, or absolute value of 1 over square root capital N. Dimensions are n by n, so this n by n matrix. I just want to make sure the entries are all roughly the same magnitude, and that's all I need to know. Okay, but yeah, it's omega to the ij when omega is e to the 2 pi I over n. So two different i's here, but anyway, so this is all I need to know. And the question I'm asking is this again. So let's summarize. But the question is, I have this big matrix, and I'm choosing my A by taking a random subset of the rows. And I want to ask, is that A good? Is that A good? And how many rows do I need for that A to be good? Okay. So this is a more delicate question because the matrix I'm dealing with now is not just a random matrix. Okay, the rows are all taken from the same collection of rows, namely they're all taken from M. Is that a good matrix? As I was saying before, this has some applications. So in some applications, you're kind of forced to use this matrix. In some applications, MRI, ultrasound imaging, this matrix just shows up from the application. You have no choice. You cannot choose another matrix. And another advantage of using this matrix is that, as I was saying, it's very efficient. So you could, this operation of sparse recovery can now be done very efficiently. Because it involves matrix multiplications, which is something you can do very efficiently once you have fast Fourier transform. So this was a question that people looked at. Let me not try to further motivate it. And there are lots of known upper bounds. So this started from the original paper, Candes and Tao. They showed the worst bound of k log the power 6n. So remember, this is like what the random matrix gives you. This was improved later by Rudolfsson and Vershinin, and then by Chiragchi, Goswami, and Vellinker, and more recently by Bourget. And so those two last results were the best known results, and they're kind of incomparable because one is has a better exponent on the end, the other one is a better total exponent. And what we showed today is that a slightly better bound that improves on all those results. So we'll show k log squared k log n. Okay. So I'll mention towards the end of the talk that this is still not, as far as I know, this is still not the tight answer. And this is partly why I'm talking about this work here. I'm hoping that experts in chaining and other techniques would be able to maybe improve it. At the time we did this work, I knew very little about chaining. I still know very little, slightly more after today's talks. But I hope some experts will be able to see how to improve what we do here. I'll tell you more about techniques in the next few slides. I think there's hope for improvement here. At least getting rid of one more log. That would be very, very nice, I think. Okay. Oh, sorry, I should have said, yeah, definitely. We choose them randomly. Yeah, so this is a random submatrix of the Fourier matrix. Those Q rows I'm choosing here, they are random, yeah. Yeah, this is really important. Of course, there are bad ways of choosing rows, yeah. Okay. You could easily choose, for instance, you could choose rows that start with two plus 1 over square root entries. That are bad ways of doing it. So this is the result I want to show you today, and I should be able to go through most of the proof. It's not, too long. And yeah, as I was saying before, yeah, indeed, it's not. You don't have to know anything about Fourier matrix. Okay, all we need actually is this big, the mother matrix M. Has entries that are flat. All of them are roughly, say, plus minus 1 over square root n. Okay, that's all I need to know. Don't have to know anything beyond that. Okay, so let's tell you a bit about techniques before we go to the proof. So like all previous work, you can what we're doing here is like a unit bound, Chernoff, the usual kind of techniques. Basically, we're doing it in a net, using a net. So we're doing some kind of chaining here. Previous work, the way I see it, previous work took a slight detour. by going through Gaussian processes, they don't show up naturally here. That detour helped, talk about the problem, helped use kind of off-the-shelf bounds to prove certain things about the problem. But I suspect also led to the suboptimal bounds. So we actually don't use Gaussian processes. We don't use the symmetrization process. We don't use Dudley's inequality. Instead, we are kind of analyzing it in a brute force way, in a more direct way, analyzing whatever probabilistic equations show up. We might, in a sense, we might be doing Dudley implicitly. I think Jelani and I tried to figure out at some point what's really going on here, and maybe you and the other experts will figure out a better way to view what we do here. I don't know how to phrase this in the language of chaining. So instead, our proof is more in line with Bourgain's ideas, and it's I would say more elementary. In short, I'll try to convince you of that today. I mean, the whole thing at the end of the day is like 3.5 pages, and it's based on just basic probability and unit bound. So, and again, there's still something to improve. So try watch carefully. Maybe you'll see where we lost the log k. Okay. So I'll try to switch and tell you more about the math. Before I get there, yeah, let's just make sure that people are still listening. This will actually be important. So all we need here is like a very basic probability. So imagine I have a coin. I have a coin that I'm trying to was biased. I'm trying to estimate. Okay, so just a kind of basic question, basic churn of bound. I have a coin, and I want to estimate to within say plus minus epsilon the bias. So estimate to within plus minus epsilon of the bias of the coin. Like, is it half plus epsilon or half minus epsilon, right? How many times do I need to toss the coin to get 1 plus epsilon, plus minus epsilon estimate? Oh, you don't see that? Yeah, sorry, I thought this the mega should work. Okay, I can write bigger. Is it not bright enough? Or I can turn the light. Yeah. I also turn on the light, should be enough. Okay, so all I want is to estimate the bias of a coin to within plus minus epsilon. Okay. 1 over epsilon squared, great. So number of tosses, okay, is 1 over epsilon squared. This is the first fact we need. Oh, now it's getting too dark. Okay. The first fact, okay, let me put it in the middle somewhere. Okay. Oh, there's no middle point, I see. Okay, let's see. I like light. Okay. So that's very, very big, and I won't be using it much more. So 1 over epsilon squared tosses, you need to estimate plus minus epsilon. That's too much. People are gonna get. Sorry, guys. Yeah. You need sunscreen soon there. Okay. So there's no way to stabilize it, or stop. Yeah. Whatever. So that's something we all know. One more fact that we also need that's less trivial is, also not very difficult. Imagine you have a coin and you just want to know if it's like probability of heads is 0 or, 0 like epsilon, or you don't want to estimate to within epsilon, but you know it's close to epsilon. So the probability of heads is something like around epsilon, between 0 and 2 epsilon. How many tosses do you need then? 1 over epsilon, okay. So this is the second case, okay. So if, probability of heads is roughly epsilon, then you don't need 1 over epsilon. Okay, good. So let me move on, and we can go back to the slides, and now let's go see some math. Okay, good. So we have here's the setup. Just let me remind you again of the setup. We have this big mother matrix M, n by n matrix. It's flat. All the integers are roughly 1 over square root n. And we choose randomly Q. Thank you for that. That's perfect. Thanks. We choose randomly Q rows of that matrix. Okay, and then this is our matrix A. Okay, it's formed by choosing a random subset of the rows. Okay, very simple so far. You have to scale it a bit, forget about that, it will disappear in a minute anyway. And the goal is to show that for all k sparse x, remember this is what the RIP property is about, for all k sparse x, the norm of ax, the L2 norm of x, is like the norm of x. Okay? And here is the first simple but crucial observation. M is an orthogonal matrix. Okay? It's a unitary matrix. It preserves norms. So x, the norm of x, is exactly the same as norm of mx. So I can equivalently ask for the norm of ax to be the norm of mx. Okay? I didn't do anything so far, but this is a much better way to think about this condition, because, for instance, now I can replace that norm, which is just a sum of the squares. It's a norm squared, so it's a sum of the squares. I can replace it by the expectation of the squares, right? There's no difference up to, expectation is like a sum up to a normalization. And so I get the following, this is what I really wanted to remember. I get the following equivalent way to express the condition we want. I have this vector mx squared. Okay, so I take the vector mx and square all the entries. This is mx squared. The condition we want is that the expectation of the coordinates squared in the location specified by q is roughly the same as the overall expectation of the coordinates of mx squared. So this should sound familiar. This is basically some kind of sampling Chernoff kind of statement saying that I have this vector. So I have this vector mx squared. All I want to say is that for all x sparse, for all k sparse vectors x, this vector mx squared can be sampled well using those q locations. I choose q coordinates of the vector, and I want to tell you those samples sample the vector well. I'll get back to it in a minute if you didn't catch it immediately, but that's the goal for now. That will be our final goal, right? That's what we want to prove. That's equivalent to the RIP property. Okay, so I hope that's clear, and I'll get back to it. And I'll say it once more later because it's so important. So what I'm going to do next? Well, that's the usual thing. We have what a priori might look like an infinite set of vectors. There are infinitely many k-sparse vectors x, and we have to argue about all those vectors mx squared. There are infinitely many of them. How do you argue about all of them? Well, we take a finite subset, we call a net, and this, the subset should have the property any vector mx squared is close to one of the vectors in the subset. Okay, this is a net. And that's what we'll do. We'll define a finite set of vectors, H, and that forms a net, namely a set satisfying that any vector mx squared is close to one of the thing in H. Okay, so you can imagine you have this large set of vectors, all the possible vectors, mx for all x, all possible x's, and I want to take use a different color. I want to take some finite subset of this that's a net that's close to all points. The second step will be to use Chernoff bound to say that then if you take any fixed vector, so take this vector here, then with high probability when you choose q coordinates, what you see on those q coordinates of the vector is close to the overall average of the vector. Okay, remember, that's what we want to show. And now just do union bound, and you get that the same is true for all the vectors, all the vectors in your net. Okay, so that's the usual union bound, Chernoff plus union bound proof. Okay, so questions? So far, it's a good time for questions. Okay, so this is a very high level. Now let's try to go into the proof itself. And again, let me summarize. So if you lost me so far, you can come back now because recall this is what we want to prove. Okay, so we have this matrix M, this Fourier matrix or this flat orthogonal matrix. Our goal is to show that for all k-sparse vectors x, I want to show that the expectation of the coordinates of mx squared. So I have this vector. This is mx. This should be mx squared. Okay. So I have a vector mx squared. I can kind of plot it here. Some coordinates, some big, some small. And what I want to show is that if I choose q coordinates, small number of coordinates q, the expectation, the average over the q is similar to the overall expectation. Okay, that's all I want to show. And this has to hold for all k-sparse vectors x. So I have lots of these vectors. And here are two simplifying assumptions. The first one is just normalization, because it's much easier to think about it when I scale m. So let's just scale m so that the entries of m are plus minus 1. For simplicity, let's assume the entries of m are plus minus 1 and not plus minus 1 over square root n like you have in a Fourier matrix. It's just scaling. Obviously, the two sides are homogeneous in M. I can scale it. So now, from now on, let's just think of M as having entries that are plus minus 1. It's much easier to think about that. So M is a plus minus 1 matrix. Also for convenience, and this is actually crucial normalization because this allows us to think about the problem in the right way. I want to think of X as having L1 norm 1. I want the sum of the coordinates, absolute value, to be 1. Now again, this is without lots of generality. Of course, both sides are homogeneous in X, but this is actually crucial. This will be crucial in a minute. You'll see why. Maybe you can already guess why I want X1 to have L1 norm 1. This is a very useful assumption. And now notice, because we assume that X is k-sparse and has L1 norm 1, the 2 norm squared cannot be too small. Right? So if I assume the L1 norm is 1, how small can be the 2 norm? Well, the flatter the vector, the smaller the 2 norm would be. But in this case, we know the vector is k-sparse. So the worst case is when all the entries of the vector are exactly 1 over square root k. Okay? 1 over k, in which case the sum of squares is 1 over k. So what we know is that, keep this in mind, we know that the L2 norm squared of X is at least 1 over k. And that's actually all I need to know about X. I don't care about X being sparse. Okay, this is how the problem was formulated originally, but actually I don't care that X is k-sparse. All I care about is that the 2 norm squared of X is not too small. It's at least 1 over k. We'll use it in a minute. So that's the setup. That's all we want to show. And as I was saying, we're going to use a net. I have to define a net of vectors that cover or nearly cover all the space of all vectors mx squared. And the way we'll do that is using, again, Chernoff, but it's Chernoff in a different place in the proof. Basically, we'll do the following. This is the most crucial observation here. We notice that because x1 has L1 norm 1, well, if the sum of the coordinates is 1, we can really think of X as a probability distribution. Okay, so I'm saying something very basic, but it's a really crucial realization here. If you have a vector whose sum of coordinates is 1, you could think of it as representing some probability distribution. There's the issue of signs, but ignore that. Imagine that X is positive. That doesn't really add any difficulty. So because we can think of X as a probability distribution, well, Mx, what is Mx? Well, Mx is an average, some expectation of some average or convex combination, I should say, of some columns of M. And this is a very useful realization because now, using Chernoff, I can say that whenever I have a vector x, this of L1 norm 1, I can think of Mx as being some average of columns of x, and hence I can approximate Mx by taking sample of columns from that distribution. Okay, so there are lots of distributions out there, but I can always sample from whatever distribution I get. And the crucial thing is that because I only take a small number of samples, the number of possible vectors I can get that way is small. It's only n is the number of columns here, to the power number of samples. Okay, that's the number of way to choose. Number of way to choose 10 columns here is n to the 10, and that's what I'm using here. So let me demonstrate this. Okay, so here's my my Hadamard matrix on the left. Okay, so it's a plus minus 1 matrix. It's orthogonal. And here is a vector that has L1 norm 1. You see the sum of the coordinates of the vector is 1, 0.1 plus 0.7. Yeah, it's 1. And that's what the product is. M times X is the vector there. Now, what I want to show you is that I can replace the vector by a vector chosen from a small set. And the way I'll do it is basically assemble from that distribution that's given by the vector. So the distribution gives some probability 70% to the fourth coordinate and so on. So if I sample from it, let's imagine I sample 3 times, maybe I get fourth coordinate, maybe again fourth coordinate, and then I get the seventh coordinate. And then, so watch carefully, that's my sophisticated animation of this talk. So here's the animation. I don't know if you notice this. Let's do it again. Here. So this is the vector, and here's what happens after I sample it. I get 2/3 of my mass. 2 of my 3 samples happen to be on the 4th coordinate because it has high probabilities at 0.7. And then 1 happened to be in the 7th coordinate. And you notice that, indeed, the right-hand side is also very close. And that's, okay, you'll see that the 1 remained the 1, 0.6 became 1/3, the -0.4 became -1/3. Again, this Chernoff, of course, it's not too surprising, but the important thing is now I managed to bound the number of vectors in my set, right? There's a small number of vectors in my set now because I only took 3 samples, so there are only n cube possible ways to choose such vectors. So this is the basic idea of the net. So far, nothing probably too surprising. I hope it's clear so far. So questions? Okay. So that's, so basically I managed to tell you, initially we were worried about all those vectors mx squared. Now I'm telling you there are actually not that many of them. Here's the bounded number of such vectors. And now you just have to take those vectors, this net you constructed, and then show that for all vectors in the net, sampling coordinates of the vectors, which is what we care about, works well. So you have to take union bound over all the vectors in the net. Okay? So you can notice there are 2 Chernoffs happening here. One is here in constructing the net, and the second is in showing that choosing coordinates of the vector works well, okay, in the bound on Q. So there are 2 things going on here. Okay, so this sounds very good, but like all good things, it's slightly oversimplified, and you'll see in a minute why. But let's just try to implement this idea and see what numbers we get. Okay, so let's start with the simplest case. So again, we have all those vectors mx squared that we want to argue about. Let's start with a case when the vector mx squared is kind of flat. By flat, I mean that all the coordinates are roughly 1/k. Remember, we know that the average of the coordinates is 1/k. We know that because x is k sparse, so the L2 norm is not too small. Okay, so now I have the vector mx squared. Okay, and imagine it's kind of flat. Imagine that all the coordinates are roughly 1/k. Okay, this is the easiest case to handle. And now let's start to understand how many samples I need to take from M in order to approximate this vector well. In other words, how big is my net going to be, right? I have to now approximate this vector using a sample of columns from M. Okay? And to approximate such a vector well, you really want each coordinate, or roughly coordinates, to be approximated to within 1/k. Because the coordinates are kind of pretty small here, roughly on the order of 1/k. So you want to approximate the vector well, you want an approximation of plus minus 1/k in each coordinate. And so how many samples do you think you'll need for that? Remember, M is a plus minus 1 matrix. Okay? And I want to sample from M and get approximation to within 1/k of each, roughly, of each coordinate. How many samples we need for that? We already have some parts on the board here, for those of you who can see that. K. Not k squared? Okay. So, good. So it is k. Well, actually, you can see that. It's just, must be the sun. Yeah. So, Beamer is so sophisticated. So yeah, so k samples suffice, but it's not because of number 2. It's actually because of number 1. It was a trick question. So yeah, it's you might think it's because of number 2, but actually, if you think about this, M is actually plus minus 1 matrix, and I'm trying to estimate something that's close to 0 here. Okay, so kind of in the middle of the range. You might say, oh, actually, I need 1/epsilon squared, or I need k squared samples. Well, it turns out I need k samples because this is mx squared. Okay, this is the square of mx, and what we're actually approximating with our sample is mx. So to approximate mx squared to within 1/k, I only need the 1/√k approximation of mx. Okay, so luckily here I'm only getting k samples, and k samples indeed suffice. So with k samples, I can approximate mx to within plus minus 1/√k. Well, but luckily we're squaring it, so this gives us approximation to within 1/k, which is what we need. So what's the bottom line of this whole story? It says the size of the net, in this case, for the flat vectors is n to the power k. Okay? So the net is rather big, But you see, this still gives a good bound. The net is of size n to the k. But now we have to get to the second part of the argument. Now we know that we have a kind of finite number of vectors to worry about, only n to the k. But we can ask ourselves, for those vectors, how many coordinates do I need to choose to get a good estimate of their expectation? And those vectors are flat. All the coordinates are roughly the same. So you really don't need that many samples. In fact, a constant number of samples, a constant number of coordinates will give you a good, good feeling for the average, okay? And so this is, again, basically number 1, I guess, with a constant epsilon. So if I only want some 10% estimate of the expectation here, a constant number of samples should be enough. But of course, I have to take union bound over n to the k things, so I really need good confidence. So I need to take q, the number of samples, number of coordinates, to be k log n. K log n would give me a high enough confidence, namely confidence n to the minus k, that I can then take union bound over all n to the k vectors. Okay? So k log n is fantastic, right? We are shooting for k log n log squared k. So this is, k log n is fantastic. Unfortunately, that's not the end of the story. There's more to the bound than this. But this is just a warm-up. So we dealt with the case of flat vectors. Any questions about flat case? So this was the flat case. Now let's go switch to the more interesting case, the case of a peaked vector. So again, remember the vectors we have here, those vectors have the expectation is 1 over k, and they're kind of between 0 and 1. So this is the kind of the other extreme case, when there's 1 over k fraction of the coordinates that are roughly 1, somewhere in the area of 1, and the others are 0, say. Okay, this is what I call a peaked vector. Yeah.
I guess I have a question about this empirical method. So if we just apply it instead of Fourier matrix, the usual Gaussian matrix, would we know that around k log n rows are sufficient to approximate the normal whole vector not to spread, not necessarily concentrated to exactly k?
So you want to apply to the random Gaussian case?
Yeah, so I mean, for the usual arithmetic, we would just strictly take like nets in this like k
Right.
plus subset.
Right.
Using argument like this gives like more detailed results maybe?
Yeah, so you're saying the usual bounds really need k sparsity? They won't work? Yeah, this is more general because I just need something about the L2 norm, yeah, or the L1 norm. Yeah, it should, yeah. Because I'm really not using sparseness, sparsity, yeah. I'd be surprised if it's not known though, but yeah, it's true. So here things get slightly more interesting because here, so I have this peaked vector. And let's go back to constructing the net. I want to construct a good net for this vector. Now, because the vector actually has the coordinates that I care about are actually quite large, I don't need a very good precision. I don't need to get things within 1 over k like before. I can easily get the coordinates approximate to within 1/10, okay, plus minus 1/10, which is great because it means the net will be smaller. And indeed, I can do that using only, by Chernoff, I only need a constant number of samples from the columns of M to approximate any such peaked vector. So the net seems like it should be pretty small. One thing, though, that's going to kill me here is that if I only approximate coordinates to within plus minus 1/10, all those 0 coordinates will suddenly look like they're 1/10, and then the whole thing gets flooded by the 0 coordinates. I'll be the expected coordinate suddenly becomes, instead of 1 over k, will become like 1/10 because there's all those 0 guys. You see the error bar is quite big. All the 0 guys will produce some noise. I'll be seeing the noise instead of seeing the actual signal. So what we'll do to fix that is actually quite intuitive. We threshold the result. So this is slightly more sophisticated net construction. We're saying, let's do the usual net construction. Let's sample from the columns of M. But after you average them, apply a threshold. I want to ignore all the coordinates that are below, one quarter. Okay, so anything below 1/4, I ignore. I don't care about the coordinates. Okay, because remember, I assume the vector is peaked. So what I care about are actually coordinates that are really big, close to 1. So, and I assume anything below 1/4 is probably noise. I don't want to worry about this. Even when you do that, you have to be a bit careful because you have false positives, right? There are tons of those small coordinates, tons of those 0 coordinates, and once in a while, approximating to within 1/10, but once in a while the big coordinate shoots up. So I want to make sure that the fraction of coordinates that shoots up and goes above 1/4 is small enough. Namely, it should be less than 1/k, so it doesn't, it doesn't flood my existing signal. I have those 1/k coordinates. I want them to dominate. And well, for that, all you need to do is make sure that you have less than 1/k false positives, and that you can achieve using low k samples. So this is one place where low k, this is the first time where low k shows up here. Once you have low k samples of columns of M, you know that the fraction of false positives is going to be much less than 1/k. So it won't affect the overall answer. Bottom line, we get a net, for this case, for peaked vectors, we get a net of size n to the log k, okay? So we have a net that's quite small, n to the log k is quite small. And what we need to do now is go to the second part of the argument. We have the net, we have a small number of vectors. We want to understand how many coordinates we need to sample in order to approximate them well, okay? Now those vectors are harder to sample because they're so peaked, right? I cannot just take a constant number of coordinates and hope that I sample the vectors well, because the constant number of coordinates won't fall in that small area. So I need something like k samples, k coordinates, in order to sample them well. Now this is number. Now this is again number 2. This is number 2, right? So I'm trying to hit a small area of 1/k and get a good estimate of the fraction of coordinates there. So I need something like k samples. And indeed, I have to remember I have to take also union bound over all vectors in the net over all n to the log k. So in total, I get k log n. Okay, so the log k log n comes from the net, and the k comes from estimating the coordinates for the number of samples I need to hit the small peaked area. So I hope that was somewhat clear. You see, in the previous case, we got k log n, because it was this extreme case. Typically, what you get is k log n. That's the number of coordinates you get. So where does the other log k come? Remember, the result we have is k log squared k log n. Well, the other log k, unfortunately, comes because there are cases in between these two cases. And the hard case, and it's something that I'm sure you've seen before such problems, is that hard case is when you have like a little bit here, a little bit there, and so on. There are all those scales, and each scale gets a little bit of mass. And the hard case here is there's the like 1/log k mass on the peaked, another 1/log k on the scale below it, like half, another 1/log k on the scale below it, like 1/4, and so on. So all these scales show up simultaneously, and then we're losing a log k. I don't know if it's necessary. That would be really nice to get rid of that extra log k. But the way we do it is by constructing several nets. Each net is responsible for a different part of the vector. So we take the vector and we write as a sum of vectors, each one of a different scale. We take the peaked area and the area where it's roughly 1, area where it's half, quarter, 1/8, and so on. And this is why we lose another log k, because there are log k nets here that we have to worry about. But at the end of the day, we show that if q is k log squared k log n, that q suffices to approximate all the vectors in all the nets simultaneously, and then we're done. Yes, that's the end of the proof overview. So questions so far? Okay, so I hope roughly so. There's some kind of magic here that even though as the scale changes, we saw the two extremes, right? The peak case and the flat case, the two things kind of balance very nicely, namely the number of vectors in the net, right? In the flat case, we had the much bigger net. In the peak case, it was much smaller net. But that number exactly cancels or balances with the number of samples that you need to take in order to sample well those vectors. So, I mean, that's a nice thing. The two things balance so nicely. So back to PowerPoint. Maybe there's a point here. So one thing I didn't tell you is that how things depend on epsilon. I want to hide this extra parameter. If you care about this, if this is something you care about. In most previous work, dependence on epsilon is like epsilon to the -2, because there's a quadratic dependence on 1/epsilon. In Bourgain's work, it was worse. I think he just didn't care. It was 1/epsilon to the 6. The proof I just told you now, if you do it carefully and figure out the epsilon, you get epsilon to the -4. And if you work a bit harder, you can get epsilon, you can get back the dependence, the quadratic dependence on epsilon, up to some logarithmic terms. And some of it requires work, which is something I don't fully understand, because in previous work it was automatic. You just get the epsilon squared. And here we had to work some extra work to get the epsilon squared dependence. Just an anecdote, I don't know why. So to summarize, the open questions are, this is what we proved. We proved that if you take a Fourier matrix and you sample k log squared, k log n random rows of that matrix, that's going to give you an RIP matrix. It has the RIP property, namely any k columns of that submatrix are going to be roughly orthonormal. Okay? And the best known lower bound is k log n, due to Bandera, Lewis, and Mixon, and it would be nice to close that gap. I'm hopeful that at least one extra log k can be shaved off our bound, and I try to give you intuition why we get those 2 log k's. Maybe you'll see how to get rid of one. It'd be really nice. And another question is, I mentioned briefly before, can we try to combine the 2 techniques or understand what's going on here in terms of the Gaussian framework, Ulus and Vershinin, because the whole paper is written in a very different language. And maybe you can get the best of both worlds. I don't know. But this would be nice to figure out. So I think I'll stop there. Thank you.
How is this K-log lower bound different than standard lower bound for any arithmetic? It's like it doesn't come over k?
Yeah.
No, but that still can't be true if k is very close to n, right?
Okay, so I had a discussion with Eric before. The reason it's true is because of the...
There's like very certain range of k's for which it is better.
No. I think the issue here is repetition versus non-repetition. I think for this lower bound, we should... Okay, for most work it doesn't matter, also for us it doesn't matter. But I think for those lower bounds you might care about it. We choose with repetition, and I think when you do repetition you might care about, they might be different. I know the case.
So the lower bound is for random choice of rows, it's not like for any choice,
It's always for random choice of rows. I'm just saying, do you choose with repetition or without? So when k is very big, this is important, because if k is like n, and you choose without repetition, just get the whole matrix, and it's great, it's orthogonal. But if you choose n random rows with repetition from an n by n matrix, it won't be exactly orthogonal, right? Without having to worry about the object. Yeah, you go on right here. Yes. Okay.
Just a comment related to Ilya's first question. So I just want to say we'll see in the next talk. So the question was, you don't just preserve k-source vectors, you preserve these vectors just that the L1 norm is at most root k times the L2 norm. Right. And the point is, for any points at t, the number of rows, Schrodel was talking about the number of rows is gamma 2 squared of t. So gamma 2 squared of root k times the L1 ball is k log n.
That's where it's coming from.
Sorry?
That's where it's coming from.
Yeah, for Gaussian matrices.
Was it known before your work? Probably.
No, not my work. Sure we'll talk about this is like from Gordon.
Oh, Gordon's theory.
Yeah.
If you care only on one side of RIP, do you think you could get better results using this framework? There's like a lower bound instead of the other.
I don't know, good question. If I only care about the lower bound, I don't care about the upper bound.
Because I think the lower bound might be enough to show L1 color. So
I
if you
think
have
it
a cruder upper bound. Yeah, but that one could be a little bit cruder.
So maybe unit norm columns, and this one. I cannot, we have to talk offline, but.
So what is the Gaussian framework? You said maybe.
It's Gaussian processes, yeah. So they have a way of converting the question into analogous question in Gaussian processes, and then they can just apply off-the-shelf bounds, like what we heard about today, Dudley, just by analyzing those covering numbers for whatever. So this it uses some geometric analysis of those vectors you get. To get a set of vectors, you have to start covering them. So it's all. So in a sense, we're doing the same thing here. We're also constructing nets. They also have to construct nets. But kind of it seems you can do it again. You bare hands. You really see what the net is. All very explicit. You can see what the net is. They have a harder time seeing what the netting is.
What I'm confused is, like, I mean, where does the Gaussian come? Like, this is a deterministic matrix. Like,
We have experts here using Gaussians. Yeah, yeah, for me it was also magic. I didn't see the Gaussians showing up, but it's a powerful technique you can use.
One simple way to see it is after the Fourier, if you multiply a random sign thing. So for RIP, the random sign doesn't matter. Right? When you multiply the random sign, it will be nice.
That's a symmetrization. So yeah, I guess you start from Bernoulli's and then you show that you can turn them into Gaussians. That's enough to bound it out. As far as I remember.
You mentioned the exponent on the epsilon. Is it clear that the right answer should be epsilon square, or could it conceivably be smaller?
It should be clear. Yeah, I would guess it should be clear.
I think the best lower bound is epsilon square of 1 over epsilon for RP matrices.
So there's a low bound.
Yeah. But exact epsilon square lower bound, I don't think it's known.
This is Johnson-Liederschaus. Is it latent Johnson-Liederschaus?
Well, technically it's separate proof, but I guess somehow we could do it.
Okay, thanks.